So let's talk about the energy that gets stored in a magnetic field. So creating any kind of field is going to cause us to store energy, right? So if we just start out with an inductor that's got an inductance L carrying a current I, and that current is changing at a certain rate, we know that that inductor is using power. So P equals I times E. And we can talk about the self-inductance creating that EMF. So the self-inductance creating that EMF looks like this. So L times di dt. And here we're just doing the magnitude, so I've dropped that negative sign. So if we want to look at the work needed to increase the current from 0 to some non-zero value of I in the inductor, we do a little bit of work. That is how our power is changing through time, right? So that's why I use this power equation above. So if we're doing a little bit of work times power, or equaling power converting through time, then I've got something that looks like our inductance times our current times our rate of change of current. And of course, the dt has disappeared. So our work energy, or our total work that we need to do, we need to go from some zero current to some value of I. So we would do this integral. So the work that we do looks like 1/2 L I squared, right? L is just a constant in this integral up here. So I'm just doing this integral of I di from 0 to some value. All right, so our work energy theorem then would give us that this amount that we had to do to bring the current up to some value is the amount of energy that is now stored in the inductor. So the potential energy that is stored in the inductor looks like 1/2 L times I squared. So that's the energy stored in the inductor. If we take our potential energy to be 0 when our current is 0. So this is our potential energy stored in an inductor. You can go ahead and compare that to the potential energy stored in the electric field of a capacitor. That was 1/2 C times V squared, and you'll see that the form looks very similar. All right, so the energy in an inductor can be considered to be stored in its magnetic field, right? So we could say this energy right here is being stored by the creation of that magnetic field. So if we have a magnetic field of, say, an ideal solenoid, that magnetic field, the inductance of our ideal solenoid, we just figured out in a previous example, right? And I squared in an ideal solenoid. We could rearrange and write it in terms of our magnetic field and all that good stuff. So in an ideal solenoid, this is true. And whether it has an iron core or an air core, that's going to change what mu you use. And then the magnetic field in our ideal solenoid looks like this, which is where I got to I being our magnetic field times L divided by mu 0 times N. So our energy in an ideal solenoid looks like this. It has to do with the magnetic field. It has to do with what that magnetic field is going through, whether that's air or not. So that's the mu 0. And it has to do with the cross-sectional area and the length of our ideal solenoid. So since that energy is residing in the volume that's enclosed by the windings, that volume, I'll just write vol since we've used V for so many things, is that cross-sectional area times L, right? Our cross-sectional area times the length of our solenoid, right? That's the volume of our solenoid, no matter what shape we have it in. So we could write the energy per unit volume. And call it our energy density, just like we did before. So I will make sure that looks like a capital U to you guys. Our energy for our ideal solenoid looked like this. So if we divide out that volume, our energy density, or our energy per unit volume, looks like 1/2 B squared over mu 0. And that's it. That's our energy density. Right? So that is actually, we'll leave that in black font, black type. True for any region of space that has a magnetic field. So just like we figured this out for our electric field with an ideal parallel plate capacitor, we figured this out with an ideal solenoid, but it gets us down to an equation where it is true for any space where a magnetic field exists. And again, we could compare this to our electric field. So our electric field energy density looked like 1/2 epsilon 0 times the magnitude of our electric field squared. So if you go back to those notes, you can see that the form is pretty similar, right? So in this case, we have 1 over mu 0. In that case, we just had epsilon 0. And again, if the region of space is something other than free space, that mu 0 is going to become a mu that has to do with the permittivity of that material, or the permeability of that material in the case of magnetic fields. So on to RL circuits. So any real inductor is going to have some resistance, right? It's a big long winding of wire. And we've already figured out that resistance depends on the length of the wire. So our RL circuits, when we draw them, we are going to draw, even if it's the same device, the resistance and the inductance are going to be drawn separately. So let's do a thought example where we connect a battery in series. So this switch 2, we're going to have up here at position A. And we are going to close switch 1 and have the current start to flow from this source of EMF, so a battery or a power supply. So when the current starts to increase, there is going to be an electromotive force that is going to oppose the increase in current and is going to slow that increase in current. So it's not going to be a sharp increase, it's going to be more slow than that. So let's evaluate this with a Kerkoff loop rule. So my Kerkoff loop rule, I'm going to go around this loop. So I'm going to start out with our battery in series, that is our epsilon. We are going to cruise through this resistor. So as we go through that resistor, we lose I times R amount of voltage. And then we are going to go through this inductor, which the voltage drop across the inductor is going to be a negative L di dt. And that is just coming from our induced EMF being negative L di dt, right? And that gets us back to our start, so we set that equal to 0. So if I arrange this, I want to rearrange this so that I've got I's on one side and anything without an I not on that same side. So I'm going to rearrange this equation in this way, right? Okay. So let's multiply that times a dt, right? Rearrange yet again. Do a little calculus here. Little differential equations. So we'll say IR dt and dt. All right, so we're gonna keep on going. Let's take this over to the other side. I could rearrange that equation that I wrote on the previous slide to look like this. And like I said, I kind of want to get all the i's in the same place and all the things that are not I in a different place. So I've got something that looks like this, which doesn't really make too much sense. But remember, we were closing our switch to go from I equals 0 to some other value of I. And really, to be correct, I should give this a mark in the current there to say that those i's are different than the I on the integral. And we timed it so that we closed the switch. So just when we closed the switch, current was 0, and we called it time equals 0, and going to some later time that we call t when we have this current I. So when you do that integral, you get some very ugly stuff. So on one side, you get negative 1 over r times a natural log of epsilon minus IR over epsilon. And on this side, you just get T over L. Right? So as you do the work of rearranging this, and I'll just give you a dot, 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 you're going to get to a point where you have that should be a 1. So I have 1 minus the natural number to the negative t, and I'm going to say over tau. And in this case, our tau for this kind of circuit is L over R. So this guy is our time constant for this type of circuit, for an LR circuit or an RL circuit. They get called both things. And this is our current. This is how our current would increase from 0. So that's what this case right here is that you see on the graph to the left. So after that first switch is thrown closed and t equals 0, the current increases towards a maximum value, right? Our maximum value would be this E over R. Because at long time intervals, after the circuit has stopped changing, after the current has stopped changing, the inductor is just holding a magnetic field. It's not resisting a change in current as the current reaches that steady state. What about the other way? So the other way, or the next step that they tell us to take, is to flip the switch to this position B. So just before we flip that switch, we had that steady state current at its maximum value of epsilon over R going through our circuit, right? And so now our inductor is going to resist the change in our current back down towards 0. So again, we want to write a Kerkoff loop rule equation. So our Kerkoff loop rule equation, as we go around this loop, is going to be the inductance and the EMF through the inductor and the EMF through the resistor equal to 0. And again, we could attach negative signs to both of those, but if it's going to be equal to 0, we could also make them both positive. So I've written it that way. So if we rearrange and let's write the right thing. If we rearrange this equation on the top, we can collect all the i's on one side and all the things that are not I on the other side. And then we can do an integral. So we want to give ourselves the idea that the moment before the switch is switched, our current, we could call it I0, but that's the epsilon over R, the maximum steady state current that we were going to reach. Okay, so if you do this integral from something to nothing and from t equals 0 to some later time, you are going to come out with an equation that looks like I0 e to the negative t over tau. And again, that tau is your inductance divided by the resistance for this inductor circuit. So this is an exponential decay. So this exponential decay looks like this over here. That epsilon over R was what I labeled I0. But this equation that is plotted right here, we'll write it in their terms with the epsilon over R. And this, again, we want to make sure we're using it in the right place. So this is our time constant, tau. And this I is our current. When we're reducing our current to 0. So when we open a switch or take a battery out. So you could think of these as your reaction time as the resistor inductor circuit is turned on and off, right? So the time constant of our circuit we could think of as our reaction time. It is L over R. Remember for our RC circuit, our time constant was R times C. So for our inductor, we've got a 1 over R relationship. For a capacitor, we've got a times R relationship, proportional to R. Good to remember those two things.